Okay, let's go ahead and get started. Maybe just one administrative announcement. I usually have my office hours on Fridays from 2 to 3. Someone scheduled a meeting for me at 2:30. So if you are planning on coming to my office hours, actually, you could just talk to me after class right now at 1:30. If you want, I'm free then, or you could come right at 2. That would let me make this meeting. I found that most people don't actually come to office hours. I usually just sit there and I'm very lonely, but that's okay. It's fine. I like being lonely. I have 2 kids under the age of 3, so I can use the alone time. Okay, good. Enough about me. Today, I want to finish our discussion of the general theory of relativity and move on to the subject of cosmology. So, before moving on to cosmology, however, I would like to discuss one more interesting and very important aspect of the theory of general relativity, which is one that's not just cool and interesting, but it's a subject that you, as you go through your lives as physicists, may end up hearing quite a bit about, because I think this is really an up-and-coming new area of physics that is going to get very exciting in the next decade or two. Okay. So, in order to understand a little bit about gravity waves, let me first just remind you of something that you already know very well, which is that the equations of electromagnetism allow for propagating wave solutions. This is something that we have discussed several times in this class. In particular, it was one of the primary motivations for the development of the special theory of relativity. And in particular, we give a special name to these electromagnetic waves. We call it light. And the properties of the equations of motion of electromagnetism, among other things, implied that the speed of light was constant to in all reference frames. Okay. And just as the equations of electromagnetism allow for propagating wave solutions, the equations of general relativity, namely of gravity, also allow for propagating waves. And such waves are known as gravity waves. And you should literally think of them as a ripple in the geometry of space-time, or a ripple in the metric of space-time. More specifically, if you think about what space looks like in the absence of gravity, then if you have a pair of events separated by some time separation dx and spatial separations, some time separation dt and spatial separations dx, dy, and dz, then the invariant interval between two events is given by our usual formula in special relativity, minus c squared dt squared plus dx squared plus dy squared plus dz squared. And in the presence of a gravity wave, this expression will be modified slightly to include a term that describes a ripple in the geometry of space. So, of course, I don't want to go through the equations of motion of general relativity and derive it for you. Instead, I'll just tell you a little bit about what it looks like. So, for example, if we have a gravity wave moving in the z direction, then the invariant interval of special relativity is modified slightly. And in particular, it will pick up a term which is a constant. Here, I'll just write it on the next line so that I have enough room. Which is a constant times cosine omega t times dx squared minus dy squared. So that's one possible sort of gravity wave. Okay. This constant A is referred to as the amplitude of the gravity wave. Omega is the frequency of the gravity wave. And what one can see is that this deviation from our usual expression for the invariant interval will change, for example, the proper distances between events as this gravity wave passes by. Okay. So let's now try and use this expression for the invariant interval in the presence of a gravity wave to understand exactly what it would look like if we were here in this classroom and suddenly a gravity wave passed by that would disrupt the geometry of space in this classroom. Yes, question?
Is there any specific reason it's dx squared minus dy squared?
I will discuss that in just a minute. Okay. Indeed, there's a dx squared minus dy squared. Okay. That is a special feature of gravity waves. I can't actually prove to you why that's the case, okay? But what we're going to do is we're going to understand exactly what that means for the physics of gravity waves in just a minute. Yes, there is a reason for that, and it has an implication that we're just about to work out. Okay. But before we do so, let me just remind you of how things work for the simpler case of electromagnetic waves. So let's imagine that we have an electromagnetic wave. And let's say that, as in the case of the gravity wave that I just wrote down, let's say that we have an electromagnetic wave moving in the z direction. Then that means that the electric field will change in time, and it'll be proportional to cosine omega t, where omega is the frequency of the wave, times some vector which tells you about the polarization of the wave. So, for example, there's one electromagnetic wave where E would point in the x direction, and it would oscillate like cosine omega t. And there's another sort of electromagnetic wave which would look like cosine omega t times y hat. So there the electric field would point in the y direction and oscillate as a function of time. Or, of course, there could be a more complicated polarization where it points in some combination of the x and y directions. And that would lead to, for example, circularly polarized light or something else, which you probably have seen, hopefully, in your waves classes or your electromagnetism classes. Have you seen polarizations of light? Okay, good. Have you seen circularly polarized? Okay, you're not going to see it here. Okay, so how would we observe a light wave that was traveling through this room? How would we observe an electromagnetic wave? Well, one thing that we might want to do to observe it is we might want to set up a experimental apparatus sitting in the xy plane where we just have a bunch of charged particles, electrons or protons or something like that. And then, as this electromagnetic wave moves by, these charged particles are going to wiggle back and forth because they'll be subject to some electric fields that are oscillating as a function of time. So, for example, if E is cosine omega t times x hat, the charges wiggle back and forth in the x direction with frequency omega as one of these charged particles passes by. As one of these electromagnetic waves passes by. Okay. So that's what happens when you have electromagnetic waves. What about a gravity wave? Okay. So let's now consider this gravity wave. So the metric, that is to say the invariant interval, is the usual thing, plus a correction term that depends on time. And so let's imagine how we would observe this. So what do you use the invariant interval for? Well, among other things, the invariant interval is what you use to measure the distance between 2 points. The proper distance between 2 points is found by calculating the invariant interval between those 2 points. So if you have 2 points at the same time in some coordinate system, then the invariant interval just gives you the usual Pythagorean theorem that determines the length between 2 points. The length squared is the sum of the difference in the x direction squared and the difference in the y direction squared. Okay. So let's now imagine that we have our same experiment where we have a bunch of charged particles in the x and the y direction. And you know what I'm going to do is I'm actually not going to have a square lattice of charged particles. Just to make the picture a little clearer, I'm going to imagine that we have a circular hoop. Okay? It's a hula hoop. Okay, there's your hula hoop. So let's imagine that we start at a time, say, t equals to pi over 2 omega, where cosine omega t is equal to 0. Then we have our circular hoop here. Okay. So at time t is equal to, I could have also started at time t equals 0 or time t equals 120 billion, but let's just start at time t is equal to pi over 2 omega, where cosine omega t is equal to 0. The metric is exactly that of flat space, and our circular hula hoop is a circle. Then let's wait a little bit of time. Let's wait, for example, till we're at time which is equal to pi over omega instead of pi over 2 omega. Okay. In that case, cosine omega t is equal to minus 1. And what we see then is that our metric looks like dx squared plus dy squared minus a little bit times dx squared plus a little bit times dy squared. So what does that mean? That means that our hula hoop is squashed. The distance between points, did I draw that correctly? No, I actually drew it the wrong way. It's going to be squashed in the x direction because the coefficient of dx squared in the metric is smaller and the coefficient of dy squared is bigger. So it's going to look a little like that. Okay. Because the coordinates of this hula hoop in the xy plane are not changing, but the proper distance between the points on the hula hoop in the x direction are getting squashed a little bit and stretched in the y direction. And then at time 3 pi over 2 omega, we're back to a circle again, because that cosine is equal to 0. And then, I'm sorry, I've run out of room here. At time equals to 2 pi over omega, the coefficient of dy squared will get reduced and the coefficient of dx squared will get increased. And so you'll be squashed in the y direction and stretched in the x direction. And then you'll go back to a circle, and then you'll be stretched in the y direction again, and so on and so forth. So what happens to our hula hoop as a gravity wave passes by is that it's going to get alternately stretched in the x direction and squashed in the y direction, and squashed in the x direction and stretched in the y direction. Unless I said that backwards. Okay. It's going to get alternately stretched and squashed. So as the gravity wave passes by, the actual distances between the edges of the hula hoop will change in time. Not really because the hula hoop is changing, but because space itself is getting stretched and squashed as this gravity wave passes by. So just to get back to a question that was asked earlier, the reason why you have this stretching of one direction and squashing of the other is that you had this relative minus sign. It was dx squared minus dy squared instead of dx squared plus dy squared. And that's just a feature of general relativity. Okay. It's telling you that this gravity wave is coming with a sort of polarization. And it's a polarization that doesn't stretch everything at once or squash everything at once. It stretches one direction and squashes the other direction. Okay. And this is known as a plus polarized gravity wave. Why is it called a plus polarized gravity wave? Well, you sort of look at that thing and you look at that thing and you imagine them superimposed on top of each other and it looks a little bit like a plus. Okay. That's just what people call it. Yes, the question.
I was going to say, what are the main sources of gravity?
We'll talk. I'm going to get to that. So after I discuss the basic features of them, I'll talk about how we are going to detect them and what we think might cause them. Okay. Yes.
So you can't get it polarized in every direction. So
that's right.
Space.
You can't. There's no such thing as a gravity wave that will make the hula hoop shrink and then grow and shrink and then grow. Okay. That's just not allowed by the equations of general relativity. So, for example, among other things, general relativity makes a prediction for the sorts of gravity waves that we'll see. Now, of course, there's a second sort of polarization that we could think about. So just as with electromagnetism, you could have waves that are polarized in the x direction and do nothing in the y direction, or waves that are polarized in the y direction and do nothing in the x direction. In addition to plus polarized gravity waves, you can have cross polarized gravity waves, where you start with a circular hula hoop and then it gets stretched alternately in the 45-degree lines in the x plus y direction or in the x minus y direction. So, and just as there are two polarizations for electromagnetic waves, there are two polarizations for gravity waves. And this is actually what would happen to a hula hoop if a gravity wave passed by. Yes?
Isn't it the same thing, but you just turn your head 45 degrees?
Yeah, absolutely.
Why give them two names?
Well, why do you call x? Isn't x and y the same thing if you rotate your head 90 degrees? Okay. You should ask the person who said that there are two polarizations of an electromagnetic wave, x and y. Okay. Because x and y are the same if you rotate 90 degrees. And these cross polarization is the same as the plus. You just rotate your head 45 degrees. Absolutely. Okay. The point really is not that these two different names are particularly important, but the point is that there's two different possibilities. Okay. Once you fix your point of view, once you fix your x and y axes, then there are two different possible polarizations possible. You could call them plus and cross. You could call them plus rotated by a little bit and cross rotated by a little bit if you wanted to define two new symbols. But this is just sort of the convention. Yeah. Question?
So this deformation is relative to the flat space?
This is the deformation relative to flat space. So what we do is we imagine that we measure the the question you can sort of wrap your mind into knots if you start about thinking how do you actually know that it's flat space in the first place. Okay.
If it is relative to flat space,
yeah.
so we cannot really measure. We cannot really see.
Right. I mean, what you really, the point is that we could start with a hula hoop here. And the hula hoop, we would say that it's a circle. But the reason why you say that it's a circle is because you believe that space is actually absolutely flat. Space is not actually absolutely flat. Okay. And so this is only true, the picture that I've written down is only true in some approximation. But, for the point of view of experiments like this, what we really care about is the time dependence of this. Okay. So, for example, there is currently a gravity wave detector that is in operation, which is called LIGO. Okay. That's Laser Interferometry Gravitational Observatory. Okay. So what is LIGO? So LIGO is an experiment where you have, it's simple to describe. It's an experiment where you have a pair of mirrors. You have one mirror there and another mirror here. And you have some sort of interferometer here. And you've got a pair of lasers. Physics is always better with lasers. Which are bouncing back and forth between these two mirrors and the interferometer. And we don't actually, getting back to your question, we don't actually care about the absolute distance between the interferometer and the two mirrors at either ends of these legs of LIGO. We only care about the relative change in the distance between these two legs. So, in particular, even though it's actually rather difficult to measure the absolute distance between, say, the interferometer over here and the mirror over here, you can easily measure whether or not that horizontal distance is changing a lot compared to the vertical distance. The distance in the x direction is changing with respect to the distance in the y direction. How do you do that? Well, you have this interferometer where you're interfering these two light waves with each other, these two laser beams with each other, and you get a particular interference pattern. And then, if there is a gravity wave that passes by, that would change the distances between on the x leg and the y leg of this apparatus. That would cause the interference pattern to change. And so, in fact, the sensitivity of this experiment is really impressive. The lengths of the two different legs of this apparatus are about 1 kilometer. And by using interferometry, variations in the length can be detected at an accuracy of about 10 to the minus 16 centimeters. Okay. That's pretty impressive. Okay. Try and measure something with an accuracy of 10 to the minus 16 centimeters, and you'll discover it's actually pretty hard. And they can do it because they can do this very, very delicate interferometry between the two different laser beams. Okay. Question? No, you're just holding your hand up. Question?
You said the length is 1 kilometer. Length of what exactly?
The length, this length here. Okay, so this length is about 1 kilometer, and this length is about 1 kilometer. Okay. And so what these buildings are is they're laser beams that you put a mirror down there a kilometer away. You shoot a laser at it, you get it bounced back. You shoot a laser a kilometer that way, get it bounced back. You have an interference pattern, and then you study the changes in time of that interference pattern, and you try and attribute that change in time to some sort of gravity wave. Yes?
Why have mirrors, not just lasers?
Good. Okay, the point is that in principle, you could have lasers a kilometer away, but you want to make sure that in order to obtain some interferometry, you want to make sure that it's the same wave that's being sent out in these two directions. So it's a lot like the Michelson-Morley experiment, actually, where you have this semi-silvered mirror that was splitting the same beam of light to go in two different directions and then bouncing back. And then because it's the exact same wave, you know that it's going to be completely in phase, unless there's some sort of something funny happening, which is making these lengths change in time. It's actually almost the identical. It's like the Michelson-Morley apparatus, almost identically, except 1,000 orders of magnitude larger. Okay, and much, much more sensitive. Good. Yes.
Did you get interference patterns with gravity waves?
Absolutely. Okay. So the question was, do gravity waves interfere with one another? And like all waves, they do. Absolutely. So for example, you could take one gravity wave with an amplitude A and plus polarization, and another gravity wave with an amplitude minus A and plus polarization. You put them on top of each other, they cancel out. So you're absolutely correct. Of course, that would be a very difficult thing to do. And at this point, of course, although this experiment is operating, it currently does not have enough sensitivity to actually see any gravity waves. And that should give you a bit of an idea of just how hard it is to see these things. Indeed, there is an ongoing upgrade to this experiment known as LIGO 2. LIGO 2. And that upgrade is expected to see actual gravity waves due to a variety of different sources. So I think the three sources that are expected to generate observable gravity waves are colliding neutron stars, or alternatively, colliding black holes. These events are actually believed to be what are responsible for gamma ray bursts, which are currently the most energetic events that we observe in the universe. Very little is known about gamma ray bursts, and so, for example, if we could correlate the observation of gamma ray bursts with the detection of gravity waves, that would give us a huge amount of information about these events. Supernovas are also expected to lead to gravity waves. So a supernova happens when a star exhausts all of its fusion energy and it collapses either into a white dwarf, a neutron star, or a black hole. When it does so, it releases a huge amount of energy. And indeed, in supernovas and in colliding neutron stars, an order 1 fraction of the mass of the star is emitted in gravity waves. Okay. Remember, what was it? 1 kilo of mass would power Montreal for a year. So if you have an order 1 fraction of the mass of a star that's being converted into energy, and that energy is being transmitted, that's a fantastically energetic event. And it's that sort of event that we would hope to see using LIGO 2. And the third source, which is one that we'll be discussing more next week when we discuss cosmology, comes from the remnant gravity waves left over from the Big Bang, which are visible in what's known as the cosmic microwave background. So those are remnants from the Big Bang at the beginning of the universe. I should probably just take a minute to talk about how difficult this is. So if you imagine what they're trying to do with LIGO 2, so the current sensitivity is not enough. For example, a detector this sensitive, measuring variations in the length of order apart in, 10 to the 24, is fantastically sensitive. It's sensitive to things like earthquakes, trucks going by, trains. It's sensitive. One of these is in Louisiana, and people shoot at it a lot because people shoot at things in Louisiana. And so actually that is one of the sources of errors that they see. They see signals when someone shoots at it. I'm serious. And actually, so in order to correct for all of these errors, they've actually built 3 of them. There are 2 operating now. I think they're building a 3rd. The idea being that if you have some gravity wave detector here, you can see that and you have a gravity wave going by, you know that it either came from up there or down there. And so if you have 2 of them on different parts of the globe, you can actually triangulate and figure out exactly where the signal is coming from. Okay. So I think there are 2, one in Louisiana, one in Washington State. And in order to build LIGO 2, what they're doing is very impressive. So for example, they're taking this entire thing and they're cooling it down to a few degrees Kelvin. Okay, sounds expensive, but that's what they're doing. That's, of course, to reduce the thermal fluctuations of the mirrors, which are now one of their biggest sources of error. So it's a fantastically amazing experiment. I should mention that, these sorts of errors, like things that are due to trains going by, these are sort of famous in physics. There was one very famous error of this sort that appeared at CERN, at the particle detector, where they were figuring out that, at certain times of day, at 12:42 every day, they had some weird error, some weird signal that they couldn't explain. And then it happened again at 1:43, and so on and so forth. And so someone finally got a train schedule and correlated it with the train schedules. And so they actually figured out that it was not a new particle that only appeared at certain times of day. It was actually a train that was going by. Okay. There was a question that, yeah.
So if you have a light wave and a gravity wave the same frequency, then how do the energies of the waves compare?
Well, remember that the energy of a wave depends on the amplitude, not on the frequency. Okay. Remember the expression for energy of an electromagnetic wave? It's the square of the electromagnetic field vector. Okay. And so, and it's actually E squared plus B squared. Okay? And so, in fact, it's not the frequency that determines the energy, but it's the amplitude. And so the question is what amplitudes you're looking at. Okay. Now, one of the reasons why these particular classes of sources are relevant for LIGO is that LIGO is sensitive to a certain amplitude, but also to a certain frequency. And so the frequency range that LIGO was built for was specifically chosen so that we could see these sorts of events. And that frequency range, of course, depends on the wavelength of the light, the laser light that you're using in this detector, because that'll tell you the frequency to which this thing is sensitive. I should pause for a second and talk about how exciting this is, because essentially everything that we know about the universe comes because of one sort of radiation. That's electromagnetic radiation. Okay. In physics, there are only 2 forces which are long-range forces that would allow for propagating waves that we could observe. Okay. One of those is are electromagnetic waves, which is light, and the other force is gravity waves. Okay. Is gravity, which would lead to gravity waves. So it's really true that when we build these detectors, we're building a telescope, okay, and we're building the first ever telescope that's sensitive to that's using a completely different medium, that's using a completely different mechanism for us to learn about the universe. And so the things that we'll learn from LIGO are completely different, and in some sense completely complementary to things that we could learn from, for example, a radio telescope or an optical telescope or an X-ray telescope. In particular, for example, if you think about the theory of the early universe, at very early times, our universe was opaque to light. Light could not propagate. So that means that in any telescope, in any detection of, in any study of the early universe based on light, based on electromagnetic waves, there's fundamentally some time before which it is impossible to probe. Because before that time, light did not propagate freely in the universe. The universe was some soup of charged particles that prevented light from propagating freely, okay? Just like the inside of a star or a planet or something like that. But using gravity waves, we can actually look back before that time. So I think it's really, I think you as physicists in your lives are probably living at the right time to see the advent of this completely new sort of astronomy, where we're able to use a completely new tool to study the universe. Yes.
Are there any estimations to know how far back gravitational waves go?
There are. I don't actually remember the answer to that. That's an excellent question, but I don't remember exactly. But I believe you can see all the way back to essentially the Big Bang. So when we discuss cosmology, starting probably not this class, but next class, we'll discuss that. Yeah. I should mention that actually there's another experiment that people are discussing building, known as LISA. So what is LISA? LISA is LIGO in space. Okay, everything's better in space. Okay, it's LIGO in space, but it's 10 to the 6th times bigger. Okay, so it's 1,000,000 kilometers on a side instead of a kilometer on a side. What is the idea here? The idea is you take 3 satellites and you arrange them in a triangle like this. And then you send, each one has 2 lasers, which are, each satellite is sending 2 laser beams to the other satellites. And they have detectors, which are receiving these laser beams. And they can perform the same sort of delicate interferometry to study the geometry of space, and in particular, how it fluctuates as a gravity wave goes by. So, among other things, the sort of things that this experiment would be able to do is it would be able to measure the angles of this triangle that has as its vertices these 3 satellites. And in particular, as we have learned, when space is curved, the sum of the angles in a triangle is no longer 180 degrees. So the way that this experiment would detect a gravity wave, among other things, is it would have these 3 satellites that are each sending out signals and measuring the angles between them. And as a gravity wave passes by, this system will find out that for a while, the sum of the angles is larger than 180 degrees, then less than 180 degrees, then larger than 180 degrees, then less than 180 degrees. And it would oscillate as this gravity wave passes by. So this is a really amazing thing. Write your member of parliament or your representative to make sure that it gets funded, because who knows. But I think it's one of the very exciting experiments that might get built in the next 10 or 20 years. So it's the sort of thing that you guys might end up working on if you end up going into this area. Again, it's a very difficult experiment. These have to be fantastically accurate, and it also has to be placed, it can't be anywhere near the Earth, so it has to be placed at one of the Lagrange points, which is like 20% behind the Earth's orbit and the Earth's trajectory around the Sun, so some tens of millions of miles away. So, this is big science. Okay. I should also mention one other statement about gravity waves, which is that although we have not seen them directly, we have already observed gravity waves indirectly. So indirect evidence for gravity waves actually comes from pulsars. In particular, as was first observed by Hulse and Taylor quite some time ago, actually, there are systems where you can have a pair of pulsars, that is to say a pair of neutron stars or a neutron star and a regular star, that are orbiting around one another. And as they orbit, they will gradually lose energy radiated away in gravity waves. And as they lose energy, the orbital period will change. It will decrease. And so, because for pulsars, you can measure the rotation period of a pulsar very, very precisely, by seeing how pulsars slow down as a function of time, you can understand how they're radiating away their energy in gravity waves. And indeed, the first observation of gravity waves, and to this date the only observation of gravity waves, comes from this indirect measurement in pulsar timing. And this is one of the best experimental checks of the theory of general relativity, for which Hulse and Taylor were awarded the Nobel Prize at least a few years ago. Okay, so this concludes everything that I wanted to say about general relativity. I think I might just take a few minutes, the last 10 minutes of class, and start talking about cosmology. But before I do so, let me pause and see if there are any questions. Okay. No? Yes?
I'm not relevant, but where are the Lagrange points?
Oh, I'm sorry. Have you guys not seen these in your mechanics class? Okay. What is a Lagrange point? If you have, let's say, the Earth orbiting around the Sun. So there's the Earth orbiting around the Sun, not the scale. There are certain points in this system. So if you are sitting at some random point in the solar system, watching the Earth and the Sun go by, you'll generally be subject to some sort of gravitational force. Okay. And however, there are certain points in the solar system where the pull of the Earth and the Sun will approximately cancel, and where your orbit will be very approximately stable. Okay. So if you want to have a very stable point to sit in a two-body system, then it's going to be at one of these Lagrange points. There are 5 of them. Some of them are easy enough to think about. So, for example, you could sit right there where the gravitational forces approximately cancel between the two. But because of the rotation, there are actually other points that you can think about where the forces approximately cancel. And they're given various names, and they're all sort of useful places from the point of view of astronomy, okay, and solar system physics. So, for example, there are places where asteroids tend to congregate. Question?
But since the solutions, the position of the Lagrange points are not exact, how is it done to build a satellite on the...
Well, yeah. I mean, these satellites will also have some sort of rockets attached to them to finally fine-tune their positions and to make sure that everything stays stable. But I don't actually know the details of how they plan to do it. You know, if you want to build a space station, then it's a good place to build a space station or something like that.
Stable relative to what? Relative to the universe or relative to our galaxy?
Relative to our solar system, you know. Because the salient question is, are you going to fall into the sun or the Earth? Or do you have to expend a lot of rocket fuel to stay exactly where you are? And the Lagrange points are places where if you could balance there absolutely precisely, you wouldn't have to expend any fuel whatsoever. But in real life, you would have to spend a small amount of fuel that's not zero, but is less than it would if you were just at some random point. Okay. When you do the Kepler problem in your classical mechanics class, you may or may not see that. Other questions? Yes. There are actually 5 single points. I'm sorry, I don't actually remember exactly where they are. You can find that one pretty easily. I don't know where the rest of them are. Okay, there's one like over here. Maybe there's some outside of the I don't outside of the plane. I don't actually remember. Okay, you can look at go look on the Wikipedia page. I'm sure that there's a good Wikipedia page. Good. Are there any other questions? Yes.
Do you plan when you see the Lagrange points of the Sun Earth?
God, you guys are really interested in Lagrange points. It's the Sun-Earth Lagrange points that they would use for LISA, but people also use the Moon-Earth Lagrange points. I think the Moon-Earth Lagrange points are all within a few 100,000 kilometers of Earth. Okay, because that's the distance between the Moon and the Earth. And so I think that the error, the reason why they want to be far from Earth because the Earth's gravitational field could muck up the experiment. Okay, and so I think this thing is going to be 1 million kilometers on a side. Okay, and so you're looking for an area of space that's approximately flat on the scale of 1 million kilometers, and the Earth obviously is not quite good enough for that. I don't know anything more about the Lagrange points than what I've so stop asking. Yeah. Any other questions? Not about Lagrange? Okay. Not about Lagrange points? Okay. So let me just begin by saying a few words about the theory of cosmology. Okay. I'm not going to give you any equations or anything like that today. So what is cosmology? Okay. Cosmology is the study of the dynamics of the universe as a whole. And in particular, when we say cosmology, we don't mean everything in the universe, because of course that's everything. But instead what we mean is the dynamics of the universe on its largest scales, where you average out and forget about the details of solar system physics, or even galaxy physics, or even clusters of galaxies physics. And you're really looking at very, very long-distance behavior of the dynamics of the universe. And in our study of cosmology, there are really 3 basic principles that allow us to really say anything at all about the structure of the universe on very large scales. Okay. And they really are different versions of what's known as the Copernican principle, which is the idea that the laws of physics are the same everywhere else as they are here. And in particular, the laws of physics are the same everywhere in the universe. You know, this is such a basic sort of idea that we very rarely actually talk about it. But if you think about it, this is really the basic assumption, the basic principle that allows us to say anything at all about our universe, aside from exactly where we are. If the laws of physics off in Alpha Centauri were very different from where they are here, then we really wouldn't be able to say anything whatsoever about this. Now, the Copernican principle is something that can be tested. We can perform experiments where we study, for example, spectral lines created by the Alpha Centauri, the star, as the elements undergo fusion in the star. You can compare those to the spectral lines that you would get for the sun and make various predictions. And you can try and test this Copernican principle. But it's important to keep in mind that it's possible that certain features of the laws of physics could be different elsewhere in the universe. So, for example, something that people worry about is the quantum of electric charge, something that could vary and have been different in the far past. Could even the speed of light have been different in the far past or different in other parts of the universe? And these are all things that one has to think about, and one should, in principle, subject to experimental test. Okay. Now, when we think about how to implement the Copernican principle in physics, we should really distinguish between 2 slightly different notions of what we mean by physics being the same everywhere. So the first thing that we might mean is that the universe is homogeneous, which is the idea that there is no preferred point in space. Namely, that no point in space should be different from any other point in space. And this should be contrasted with the notion of isotropy, which is the idea that the universe is isotropic in that there's no preferred direction in space. It's certainly possible to think of theories of physics which are homogeneous in that there are no preferred points, but not isotropic, so that there could be a preferred direction. And vice versa, it's possible to come up with theories of physics where where space is isotropic, but not homogeneous. Okay. Now, I should say, and I should really emphasize, that on short scales, on small distance scales, the universe is neither homogeneous nor isotropic. But on long distance scales, namely the distance scales appropriate for the study of the universe as a whole, where you ignore small inhomogeneities due to solar systems, galaxies, and so forth, the universe appears to be spatially homogeneous and isotropic. And these two features of the universe are the basic starting point for our theory of cosmology, which we'll be developing in much greater detail next week. Okay. Question? Yes.
I just wanted to have maybe an example of the law of physics that apply here. That is, for example, not homogeneous or not isotropic.
That is not. If, for example, the value of the electric quantum of electric charge were twice in Alpha Centauri what it is here, then that would mean that laws of physics are not homogeneous. I guess I'm out of time. Maybe I'll stop here and let people go, and you can come ask me questions. Yeah.